Okay, good afternoon. I'm pleased to be there to present you my experimentation in porting the Go concurrency model in Python. So let me quickly introduce me very rapidly. I'm a web craftsman. I'm doing consultancy and open source for a living. I'm a JUnicorn author in Python. I'm a member of the Python Foundation. And I'm also a member of the Apache CouchDB PMC and core developer of Apache CouchDB. But today I will talk to you about my experimentation of porting the concurrency model in Python. So why? Because it seems to be foolish to do that. The fact is that I'm starting to be really tired about the status quo that exists in Python. Today you have different library to handle the concurrency in Python. You have eventlet, you have a G-event, you have twisted, now tulip. But each of these library are using an event loop, are based on an event loop to manage the concurrency. They are all designed to handle mostly concurrency, but concurrency for I/O, so mostly to handle your sockets. It can be worse than that. If you use G-event, G-event is really designed to handle socket concurrency, not I/O concurrency, not file, and not playing with file. It's really bad at that. I wanted to try another thing. I wanted a real scheduler that could help me to manage any blocking work and still being able to program in a blocking fashion. I mean by that, doing a socket resave. I just do a socket resave. I don't put any callback or whatever. And the Go concurrency model seems to fit perfectly with Python. Quite the same syntax. You're coding in a blocking syntax, in a blocking manner. And anyway, using an actor model like you have in Scala or Erlang wouldn't work in Python because of the GIL, because of the thread. I will talk about that a little later. And yeah, to be honest, the real reason, it was a good distraction. A good way to learn how a scheduler works. A good way to try some stuff new, some new code. Everything at the Go in Go start from the Go memory model, and by that I mean you have two main entities in Go. You have the channel and you have the Go routine. Go routine are coroutine, mostly code that can be executed in a thread stack. So you can have multiple code in a thread that can be executed at the same times. One is running, one is living, the other are idling in the stack. The Go routine don't know from each other. I mean by that they don't share any context. They don't share any memory. They don't share any variable. The reason for that is simple. It's more easy when you isolate the code, it's more easy to put it on a thread on any core you want, because the code are isolated, they are not sharing anything. And when you really want to do some concurrency, you don't want to play with global variable. Why? Because when you check a global variable, you will lock all the scheduler, you will lock all your application just to check the state of the variable, freeze it, and getting back in your code. And you don't want to lock your code, to just do that. So to steal dialogue between Go routine, because they are isolated code, you have channel. Channel are mostly like pipe in Unix or sockets. This is a way to send or receive data between Go routine. And like on your system, you have the select that allows you to listen on multi-file descriptor or sockets. You have select and also in Go. The difference on the system, when you do a select, you are waiting for a read or write event on your socket or your file descriptor. In Go, you are waiting for a channel sending a data or a channel receiving a data. We'll show some example later. Now that you have isolated the code, now that you have the Go routine, you need a way to schedule that. On the system, you have the thread and you have the process that are the basic primitive to have concurrency on your system. Threads are just like OS processes. You can have C group on that. You can set the affinity. The POSIX threads are mostly OS process that you can embed in your application. On top of that, you have the kernel that is scheduling your work, that is telling to a thread that it can be executed, to the other thread that it can be executed, getting back the result in your app. But if you are doing something like Go, you don't want to use the system to schedule your threads. You don't want something unknown happen. You want to control your thread. You want to be able to lock all the scheduling just to garbage collect the variable, or just to stop a Go routine. So in Go, you have three entities. The main one, represented by a triangle, is an OS thread. The OS thread holds a context, a processor, context named P, which is represented by the square. The context will hold all the Go routine, all the scheduled Go routine, which is represented by a circle in yellow. So the Go scheduler is basically that. So you have context that is maintaining a list of scheduled Go routine, a queue of scheduled Go routine, execute at a time one Go routine, and a process, a context, is held by one thread. You can have multiple contexts in your app. So each thread aims maintain a context P. Each context runs at a time one Go routine, and you can set the number of contexts using the gomaxprof variable. By default, this is 3 now. It used to be 1. Now it's 3, and it generates the number of core. When you have 4 core, you will have 4 gomax, 4 process, sorry. And a context maintains the queue. So again, a process has at one time one running Go routine and maintaining a queue of future scheduled Go routine. Why having a context? A context is mostly there to allows you to run blocking code, to allows you to run multiple code, part of the code concurrently. So when you have a blocking code, what happens? When you have a blocking code, the Go routine will continue to run, and the process will be passed to another thread. And the next Go routine in the queue will be executed, which is explained by this schema. So on the left, you have a normal work, a process with a Go routine running in there, and a thread that is idling without any context attached. Then, in your Go routine, you are doing a size call. A size call can be a socket resave, or opening a file, reading a file, any blocking operation, in fact. So when your blocking operation is running, the context is passed to another thread, another M, and the next Go routine in the queue is executed. Once the size call finished, the thread will be idling, and eventually take another blocking size call later, or another process later. They are garbage collected after a time. You don't have to worry to have many threads idling in your system, because this is only 4 kilobytes of memory, which is nothing today. So when a Go routine is running, the current M makes sure that another thread is running on the same side. So you have always at a time, for one process, 2 threads running. So you can make sure that when you want to switch, when a blocking call happens, you can switch very rapidly to the new thread, the new process. You don't have to wait for launching a new thread, etc., which can be really slow on a busy system. The other reason to have context is because you want to run your work in parallel most of the time. Or rather, I don't know if you did that when you were smaller, but some of us were stealing work from the other to do more things, to do more concurrent things. So while the others were working on one task, you steal some part of the work of it and continue the work and getting further. And this is exactly what does a process today in Go. So on the left, you have one context maintained by a thread running a Go routine, and you have one other launch process in another thread that is doing nothing. You have no run queue. And rather than doing nothing, the Go scheduler decides to give him some work. So the process is stealing some work from the other process, taking some Go routing in the queue and execute one. So now you have two Go routines running at the same time on different threads. So it can be also on different core. And what's next? Basically, the Go scheduler today is a cooperative. Is doing concurrency by cooperation. So when you do a socket resave, he makes sure that he knows this is a size call, and he passes it to another process. When you are running a for, he knows that at some time you need to sleep. In 1.2, sorry, the coming version in 1 or 2 months, it will be a preemptive scheduler. So rather than waiting for an operation to schedule another Go routing, he will schedule an operation. He will schedule the Go routine each n operation. So, for example, if you are doing a 10,000 iteration in your for, on the 10,000 iteration, it will switch to another Go routine and block the other one. If you are doing a socket resave and you are doing that 10 times, after 10 times, it will go to another Go routine. And it will does that automatically, and it will be more efficient in the end. And voila, for the Go concurrency model. Implementing it in Python presents some challenge, mostly because of the GIL. The GIL exists on most script systems like Go, RuPy, or whatever, any system that are using global variable or such things. The GIL is mostly there to make sure that one thread is executed at a time. So using threads in Python doesn't mean anything, or in RuPy if you are using the default RuPy VM. Running one thread, these are true threads. So it's true they are OS threads. They are running on the different core. But the system only query one thread at a time. So you don't have any advantage to use threads. You won't parallelize your operation because of using threads, except for I/O, because I/O are handled by the system, so they can run in the background. So when you do a socket resave in a thread, it will work, and the GIL works perfectly for that. When you do a socket resave in a thread, the system will handle that in background, so you will have true parallelization of your code. And when you want to get the result, you query the thread, get the result from your socket resave, and it works. The other problem with Python is that you don't have any implementation of coroutine by default. You have the yield, so you can yield, but yield and you can yield send a yield DSF now to have some kind of Go routine system. But I find the syntax very ugly, not really intuitive, and also a yield is running on only one frame in the thread stack. So you can't really stop a socket resave or stuff like this. So because of that, I made some detailed choice to create this Go concurrency model in Python. I will have only one context per Python VM. I can have maybe multi-Python VM launch at the same time, but only one context by VM. The Go routine will be executed in the main thread. The context will be maintained in the main thread. And to do the blocking operation, so in Go, remember, when you do a blocking operation, you just switch the context to another thread. Like I said, it wouldn't work very well in Python because passing the process to the other thread will just slow down the things because of the GIL. So rather than doing that, I'm just using the thread for what they are good, for blocking operation. So instead of passing the context to another thread, I'm passing the size call, the blocking operation, to a thread, to a future, to be exact. So the Go routine will continue to will be put out the run queue, and the size call will be passed to the thread. And when the thread come back, the size call come back, I'm putting back the Go routine in the queue. So I've created a library to handle that. You can find it on my GitHub. This is compatible with Python 2.7, 3.3, 3.4, and later. Also PyPy. If you are using PyPy, you have no dependencies. And it's also using Python fiber instead of greenlets from Saguls. So I can garbage collect the Go routine very easily. So why offset? So an offset is a small and virtually complete daughter plant that has been naturally and sexually produced on the other plants. So if you know you have some plants, sometimes you have another plant that is created from this plant, and that has its own ADN. And this is the same for offset. So it's grown on top of Python, but has its own ADN based on the Go. And this is why the name offset. So I already said that. So I'm using Python fiber from Sangul. One of the things that I really like Python fiber is it is sharing the same code that you have in PyPy to handle the continulet in PyPy. So I have the same behavior in CPython or in PyPy. In PyPy, it is using the continulets, and everything is abstracted in the pros class. So eventually, later, I could maybe play with the Yale if I want to do a full CPython implementation. So in the offset scheduler, you also have three entities. You have the OS thread, which is a future handled by the Go, the concurrent API in Python 3, and you have a port in Python 2.7. The process is also existing, but one process per VM and a Go routine, the same. The difference is here. So a process is always running a Go routine. The Go routine are maintained by one process. You have only one process, and you have a feature that can be launched. In fact, you can set the number of threads that are launched. You have at a time one running Go routine and the other Go routine schedule in the context. To handle this size call, I'm doing differently from the Go. In Go, you have also a size call package that is abstracting the system calls API from the CLib or from the socket, etc., to make sure that they are on the last size call. And this is the same for me, except that I'm patch the standard library. I'm not monkey patch the standard library directly. I'm doing monkey patch in my own module named sicecall to be original. And for that, I'm using the wrapped library from Graham Doppelton, which is a very nice library to do monkey patching and to decorate your objects or class, whatever you want. A system call is handled its own system thread. Is its own thread, sorry. And everything is using the concurrent API, and you can set the number of threads using the offset max threads. It defaults to the number of CPUs by two. Sorry. And to be more clear, we'll explain using that. So on the left, you have a process running a Go routine. The Go routine entering a system call, for example, a socket resave. Then the Go routine is removed from the run queue, put out the run queue, and the system call is passed to a new thread. And then the next Go routine in the run queue is executed. Once the system call finished, once the data comes from the sockets, the Go routine is put back in the run queue and will be executed the next time. the scheduler will always wait for system call. So if you have system call running, it will wait for them to make sure that your coroutine will come back, except when the main coroutine disappears, so you have finished your code, then it will stop the scheduling. Here are some examples of using the Go routing with Go. So on the left, with offset. So on the left you have on the left you have the Python code, and on the right the Go code. So to launch a Go routine in offset, I'm using the Go function. I have a decorator main task to set the main function. So in Go, you always have a main function to execute the main to start the code. To do that in Python for now, I'm using a main task decorator, which decorates any function, and the main function will be put in the scheduler. And you have the run that starts the scheduler. So here I'm launching a Go routing. I'm launching the function say in the Go routing. This function will say 5 times hello, world, and I'm starting to the say function to say hello. So you will have 5 times hello world, hello world, hello world. And this is done concurrently because here you have time sleep. This is a time function for the time module from offset. And each time the sleep is done, the Go routine is put back in the run queue and the next one is executed. So the first time you will have the hello executed because the main Go routine, the main task is executed. Then it switches back to the scheduler, execute the Go routine to say world, and back to the scheduler, say hello, back to the scheduler, say world, etc. And you can say the same in the Go, quite the same code, in fact. Channels are fully implemented. So the way it works in offset, it is using for now a queue. A queue to collect the send, to collect the resave. When you want to send or when you want to resave, the Go routing is put out from the run queue. So, and when the message comes back, the Go routine that was sending or that was receiving is put back in the queue, in the run queue, and will be executed. So you have true concurrency. So when you are waiting to receive from a channel, another Go routine will run at the same time, which has a chance to another Go routine to send the data, for example, or stuff like it. Here is a simple example. On the left, again, you have the Python code, and on the right, you have the Go code. Here we are doing a sum on a list. We are splitting the list in 2 parts. We are creating 2 Go routines with the Go function. We are creating a channel with the make function. The sum function the only thing it does is summing the value from one array and sending the result by the channel. The 2 Go routines doing the same. Then the main task is waiting for data, so it receives in X the result from one Go routine and in Y the result from the second Go routine. Then we just print the result and sum the final result to have the final sum. And in Go, this is the same. You create your channel with the make function. Channel type in Go, but this don't make any sense to have type in Python. And the same, we are launching 2 Go routine and waiting for the result and print the result. Buffer channel are also implemented. So it can be interesting sometimes to be able for a sender to send without waiting someone receive, without blocking. So this is what our buffer channel about. You can send without waiting multiple times, and the receiver always block for results. To be clear, here is an example. Again, on the left, Python, on the right, the Go code. Here we are creating a channel with a buffer of size 2. We send 1, we send 2 without blocking this time, and we receive 1 and we receive 2 and print the results. very easy, and same in Go. Select is also implemented. The algorithm was very complicated. It took me at least 1 month to have it right, something like it. So you have 3 paths in the select. The first pass is checking if a channel is already sending or a channel is already receiving. If it's the case, return the channel that is the first channel that is receiving or sending. If not, we are queuing the current Go routing in each channel that we are selecting. And when one of the channel that we are selecting, waiting for an operation, receive or send, come back, the Go routing is put back. Then we will send the result, the channel that has sent the result first, and we are dequeuing ourselves from the other queue, so we make sure that we won't receive another data after the select. Here is an example with the Fibonacci function. Sorry. So in the main task, we are creating 2 channels. One channel that will be used to get the data, and one channel that will be used to make sure that we quit at the right time. We are launching a Go routing. In this Go routing, we are printing the first 10 Fibonacci value. And when it's done, we are sending the quit to the quit channel. And we execute the Fibonacci function. So here, until it's true, so until we don't quit, we are selecting. So we send the first value, checking if we have received the quit. If we have sent the value, then we add the value to the Y, simple Fibonacci algorithm, and getting the Y in the X. If we receive the quit, we quit. So we will here, until someone is receiving, we are sending. And when the quit is sent, we are returning. And we get the operation. And exactly the same code in Go. There are other modules implemented in offsets. So you have the basic synchronous function. All functions are atomic. I'm using the atomic macro from GCC for that, using CFFI to be compatible with PyPy and CPython. So it means that there is no real lock. We have real atomic lock. So it's really efficient, and we don't block the scheduling. We have the time module completely implemented. Coming modules are the net and I/O modules. The net module is mostly implemented. All the functions are implemented, but the API need to be done. And it will be done next week. There is another coming module that I had to write, is a module to receive system signal, without blocking the scheduler. Next thing I want to do, I forgot one thing, is adding some documentation. But I want to be able to span on multi-VM, so you have true parallelism of your system, which can be easy because Go routines are isolated. So I imagine a channel being able to speak between different OS processes, and I can send any operation to them. And I want to remove the run command because I don't find it very friendly, very convenient. So I want to remove it. So maybe I don't know how to handle the main task right now, but it should be possible. So you have everything on my GitHub repository. Any help is welcome, even for documentation. And voila, if you have some question. No. Okay.
If we don't have any questions, then thank you.
No, thank you.